This video will explain the BERT transformer model. Natural language processing has seen huge improvements by pre-training these models on massive unlabeled text datasets like Wikipedia and then fine-tuning them for tasks like question answering. This form of pre-training by constructing a supervised learning task on unlabeled data is described as self-supervised learning, and the most common form of pre-training on unlabeled text is known as language modeling. Most language models are trained by iteratively predicting the next word in a sequence autoregressively across enormous datasets of text like Wikipedia. The left to right context is the most intuitive way of understanding this, such as taking a sentence like, "The cat jumped over the fence," and iteratively predicting cat, then jumped, then over, and so on. Context can also be modeled from right to left, such as going from fence to the, to over, and so on in the previous example. Some previous models have concatenated representations learned from left to right and right to left traversals for token prediction to form representations for downstream tasks like question answering or natural language inference. BERT reformulates the language modeling pre-training task of iteratively predicting the next word in the sequence to instead incorporate bidirectional context and predict mass of intermediate tokens in the sequence and predict the masked tokens. This video will explore the details of how this is implemented, such as the exact masking strategy, exactly how the inputs are formatted to be passed into BERT, the intermediate representations of this transformer model, the BERT transformer architecture, the output, and how that's used to easily extend it to fine-tuning on sentence level and token level tasks like question answering, and how BERT is exactly fine-tuned with transfer learning. This video will explain the details behind BERT. BERT presented a new self-supervised learning task for pre-training transformers in order to fine-tune them on downstream tasks. Pre-training transformers is commonly described as analogous to transfer learning with ImageNet from computer vision. But if you're really looking to make an analogy to computer vision, it's more like pre-training with something like Google's JFT 300 million dataset or the weekly labeled billion image Instagram dataset that Facebook describes. These transformer models are making use of enormous amounts of unlabeled data, and they're training them with a self-supervised learning task. One of the key differences between BERT and prior methods of pre-training transformer models is the use of bidirectional context for language modeling. The most common form of language modeling with these large amounts of unlabeled text like Wikipedia data is to sequentially predict the next word in a left to right traversal, or do right to left as well. And sometimes you would take this representation of going left to right and you would concatenate it with the representation of right to left to form the representation for the word token. BERT instead masks intermediate tokens in the sequence for the prediction task, making the name of the bidirectional encoding. This is the strategy used in BERT in order to pre-process this massive unlabeled text dataset for the self-supervised bidirectional context mass token prediction task. So the pre-processing algorithm is going to slide through the text in the sequences of the unlabeled data, and 15% of the time it's going to select the word to be replaced according to this strategy. So 80% of the time you're going to replace the word with the mask token. It's also worth mentioning that these words are going to be tokenized. So particularly in BERT, they use the word piece tokenizer. And if you're curious about the difference between word piece and tokenizers like byte pair encoding, I recommend checking out the tokenizers blog post from Floyd Hub linked in the description of this video. When BERT is then fine-tuned on tasks like question answering, named entity recognition, or natural language inference, the mask token will no longer appear, and this may throw off the model. So in order to account for this, the selected token is also replaced with a random word or the same word with respective probabilities of 10%. The input to the BERT model is constructed to facilitate fine-tuning it for downstream tasks. So BERT pre-trains by performing two tasks. The first is the mass language modeling, where we just described having the prediction of the mass tokens, and the second is the next sentence prediction, where a binary decision is made about whether sentence B follows sentence A. Structuring the input in this way makes it easier to fine-tune BERT for tasks like question answering, where the input is formatted as a question being sentence A, and the paragraphs that contain the answer to this question is formatted as sentence B. This is also useful for fine-tuning on tasks at the sentence level, where a classifier is taken at the position at the special CLS pictured here in the pre-training task. The decision is done at this point to do something like sentiment analysis or spam detection or something like that. The original sentence is passed to BERT and then tokenized with the word piece encoder. These tokens are then added with segment embeddings. These segment embeddings signal whether the sentence is a part of sentence A or sentence B for the next sentence prediction task, or in the case of question answering, whether it's the question or the paragraphs containing the answer. In addition, they're passed with a position embedding, which denotes their place in the sentence. So this facilitates the learning process for the dot product attention by biasing it with knowledge of the sequential ordering of natural language. I highly recommend this blog post by Jay Alomar, the illustrated transformer, to get a better sense of how attention works. So we'll go through this quickly just to get a quick sense of how the BERT model is going to use dot product attention in this model. So the idea behind dot product attention is first you have the input that we've just described as having them be these tokens with the word piece tokenizer, added with the segment embedding, added with the position embedding, and then this formats the input that goes into the self-attention layers. So the way that self-attention works is you have these query keys and values, and you have weight matrices that take the original input and project them into the query key and value embedding space. So then what happens is you have this form of dot product attention. So what happens is the query matrix is multiplied by the key matrix, it's normalized by the length of the embedding, then you pass that through a softmax, and then that gets multiplied by the value. So this is the mechanism behind dot product attention that's used in the BERT model. One of the biggest questions I had when reading this paper was about how BERT would handle arbitrary length sequences, or really how transformers in general would handle arbitrary length sequences. So for the example of question answering, you might have these massive paragraphs. They can definitely be variable length with respect to the paragraphs that are inputted to the transformer. So one option could be to have a fixed length for sentences A and B, and then just zero pad the paragraphs or questions that are shorter than that fixed length. But one of the interesting characteristics of dot product attention is its ability to be flexible with the dimensions of intermediate tensors. So this is very different if you're thinking about something like convolutional network image classifiers that have fixed dimensions of the tensors throughout the network for different inputs, like a image of an airplane, an image of a cat. They all have the same intermediate tensors as they flow through that convolutional network and then get classified as cat or airplane. But in transformers, for example, if our input dimension has this sequence length by the dimension of the embedding, then you have these matrix multiplications that project this input into the query key and value matrices by having this structure of the weight matrix having this shape of the dimension of the embedding by the dimension of the key, which is also used for the query, or the dimension of the value. So when you do this final dot product matrix multiplication, you preserve the length of the original input sequence by the dimension of the key. So I thought it would be interesting, and then you also slice that final output to pass it into classification or mass language modeling. I think it's definitely really interesting to observe sort of the shape of these tensors with the transformer language model. BERT is a transformer model that follows the architecture from the paper Attention is All You Need. I've chosen to show this diagram from the evolved transformer because I think that looking at these neural architecture search algorithms that parameterize these blocks for exploration and perturbing different ways of structuring these encoder and decoder blocks is the best way to understand how they are building these structures and kind of the fundamental components of it. So the transformer blocks have the structure of using residual connections ahead of the intermediate features, and then also by using convolutions, and then having the obvious self-head attention, as well as a lot of layer normalization in the middle of these blocks in both the encoder and the decoder. Two models are described in the BERT paper, BERT base and BERT large. BERT base is the smaller version with 12 transformer blocks stacked on top of each other compared to 24, having a hidden dimension embedding of 768 compared to 1024, and then having 12 attention heads compared to 16. So these attention heads describe different parameterizations used to project the input into these query, key, and value embedding matrices. So aside from the projection, attention doesn't have extra parameters. It's this dot product of the values between the softmax of a normalized dot product between queries and keys. So the different parameters come from projecting the input into these different matrices with respect to having more attention heads. So as we talked about earlier, the BERT transformer will preserve that length of the dimension of the input, and the final output will take these vectors and pass them into separate tasks. So it will kind of like slice this output and then the CLS token position. So the input to BERT will have this special CLS token, and then the sentence A, and then this special separator token, and then sentence B. So what it does is it takes the position, like this index, at the first index by the CLS token, and it slices that representation off to pass it into the classifier that's going to do this next sentence prediction task, so saying whether sentence B would come after sentence A. These are the datasets used to train BERT in the pre-training task of having this simultaneous next sentence prediction task as well as predicting the mass tokens. So they use the two datasets, the 800 million words from the books corpus and 2.6 billion words from English Wikipedia. They use a document level corpus so they can easily extract the labels for the next sentence prediction self-supervised learning task. Also, for the sake of dataset size reference, if you're interested, the recently released Mina chatbot was trained on 40 billion words. BERT introduces a new way of doing pre-training by modeling bidirectional context and producing intermediate tokens instead of the autoregressive left-to-right task. After pre-training on something like Wikipedia, BERT is then fine-tuned for other tasks like the glue benchmark tasks in question answering, named entity recognition, and natural language inference. The BERT input-output formats makes this transition easy. One of the interesting tasks that BERT is fine-tuned on is Stanford question answering dataset. So this consists of these question paragraphs, and the BERT is trying to find the answer in the paragraph. So for example, it takes in this paragraph and has questions like, what is Southern California often abbreviated as? And it goes into the paragraph and it'll label this token. So if you remember the way that this input turns into output in BERT, basically this word token is going to be processed as start end of the answer to this question. So maybe we'll look at, so what are the ties that best describe what the 8 counties are based on? So you have in this case like a longer answer. So it's going to go into this token and then have the start prediction as the output, and then all the way into ties as the ending prediction. So it's interesting to look through this data set and get a sense of the Stanford question answering data set. The difference between Stanford question answering 2.0 compared to 1.1 is that in 2.0 they have these questions that you can't answer from the paragraph, compared to where in Stanford question answering 1.1 all of the questions contain answers in the paragraph. The BERT model is fine-tuned to output the start and end spans in the paragraph for answering this question. So the question is this sentence A embedding, and then you still have the representations of the tokens in the question, as well as the CLS, like intermediate features of this transformer model will still be updated by the gradient of an incorrect prediction, or however the loss is formulated with the start end span. So an example of this is the paragraph is this within Southern California, blah, blah, blah. This is like the paragraph that goes into this section of the input and then comes out with the same length in the output. And so basically what you're doing is you're going to slice the input to make these predictions on start and end span. So in this case of what is the population of Los Angeles, it's labeling this token as the start and end span. So there's probably a special output for that. But I just thought it was interesting to get a better visualization of how exactly the output looks in BERT. The BERT paper presents some ablations showing importance of miscellaneous things, like including the next sentence prediction task and the difference in performance compared to the original model, as well as the bigger difference, which is where you do this left to right context prediction compared to the bidirectional BERT encoding. And you see a big difference between doing that, especially when you do the no sentence prediction as well. The next ablation shows the impact of using a larger transformer model. So in this case, you see a dramatic performance difference by this language model perplexity metric compared to having like 3 transformer blocks compared to 24 or 12. Further, this ablation shows the improvement, especially in named entity recognition, fine-tuning when including the same and random words in that masked language model self-supervised task labeling. So if you remember, we had this format of 80% of the time we give it the mask compared to 10% of same or random word, and you just see the little differences between doing this and how it results in the final performance of the model. Thanks for watching this explanation of the BERT pre-training task for fine-tuning these transformer models. Hopefully from this video you got a sense of how they do this bidirectional masked language modeling, how the input and output are formatted to this transformer, and then the question answering data set, and just overall got a better sense of this kind of a transformer architecture and the pre-training and fine-tuning idea and miscellaneous details of the BERT. Thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos.